Hello, and thank you for joining us today. We're here to talk about a special issue of MRS Energy and Sustainability on large-scale energy storage and the circular economy. Our guest editors for the issue are Dr. Daniel Steingart, who is co-director of the Columbia Electrochemical Energy Center, and Stanley Thompson, associate professor of chemical metallurgy at Columbia University. He's joined by Dr. Y. Shirley Meng, the Zabel Endowed Chair Professor in Energy Technologies and Professor of Nanoengineering and Materials Science at the University of California, San Diego. She is also the Editor-in-Chief of MRS Energy and Sustainability. Dr. Jenny Baker is EPSRC Fellow and Senior Technology Transfer Fellow at Swansea University's Faculty of Science and Engineering. And lastly, we have Dr. Yongyao Xia, who is professor in the Department of Chemistry at Fudan University. Thank you all for being here. I'm going to turn it over to Dan to start the conversation.
I want to thank everyone for joining us today from really all over the world, or at least the Northern Hemisphere, to talk about our upcoming special issue for MRS Energy and Sustainability on large-scale energy storage and how it fits into circular mass and energy economy. It's a really good time for this collection. We have to make big changes over the next 2 decades at least. Decisions we make now will impact energy systems for at least 50 years, probably the next century, all over the world. So we want to make sure we do right based on the best information we have now. And even if we make mistakes, we want to be able to correct these mistakes in a as easy a fashion going forward. So it's important to have this geographic diversity. I want to mention that we would like people from all over the world to submit. We have the Northern Hemisphere very well represented. This is about the best we can do with 4 people right now. But please, wherever you are in the world, we want to understand what your large-scale energy concerns and solutions look like they're going to be. So with that, I'd like to just ask a few questions to motivate what we as the editors and guest editors would like to see in this issue, or at least the problems that we're thinking about. And so to start it off, I'd like to ask Dr. Baker and Dr. Xia, what are the critical issues that you would like to see explored in this issue? What kind of technologies, what kind of problems, what can we do with this global platform that we have?
Okay, shall I take that one first? I mean, so coming from a UK standpoint, and where we're very well integrating a lot of renewable energy into our system, but we have local grids where we can manage that demand. There's certainly questions on how are we going to store when we have excess on a diurnal basis, but also when we're looking at a 2-week period where we may be without wind. How are we going to look at that long-term and large-scale storage? Is it going to be just from linking up and having, linking up grids across Europe, or are we going to be looking at it? Is there other long-term storage that we can look at? And I think really interested to hear what solutions people have got out there, what areas they're researching in this space.
Yongyao?
I think these special issues should be closed to some potential, have a potential for the industrial applications, because we have so many sister energy storage systems. But for the large scale any renewable energy storage batteries, we should have we should choose some systems should have close to the industrial applications. I think we are issues because we have so many technologies, but some just I think is limited to now at the current states. It may be limited on the basic research.
I believe that Dr. Xia is referring to the scaling and integration challenges for batteries. I think for any other energy technologies, battery is one of the options. But I hope that in the special issues, the important topics of scaling and integration will be highlighted.
Yeah.
Yes, I think this is a good point as well to look at the balance between energy stored and the power system, and especially systems where these can be decoupled, I think is of great industrial relevance and is very important for as we're looking at grid applications as opposed to transport applications.
These are really excellent points, and as I think we're all material scientists by background. So as material scientists, we're trained to think about things that are quite small, and thinking about how these small things interact over kilometers and megatons of material is quite the challenge. In recent years, the community has begun to focus on levelized costs of storage and energy to begin to think about how to metric and baseline these types of energy storage solutions. I'm curious, and I'll start with you, Shirley. What we think about the right duration target ought to be. A few years ago, it was 4 hours. 4 hours seemed like forever. Now there's debate whether it's between 10 and 100 hours. I'm curious what you're thinking about.
Yes, I think this has been a debatable topic over quite some time. So I would say that the economic case for having a long duration storage solution is quite clear. Whether the battery is the ultimate solution for that challenge is, I think, still debatable. So I will give a simple example that UC San Diego, actually, we have a microgrid. We have like cogen turbines, and we have batteries, we have solar, we're a mini power plant. Based on my experience with the 5 megawatt-hour batteries, which is very small compared to, we're a total of 45 megawatt campus. But the operation, even for the 4 hours of the battery storage system we have, has a lot of challenges. For instance, the battery behave like a human body, like we don't do very well in the cold or hot temperature. But as you know, in Southern California, we can sometimes go to hot weathers. So actually we have to put a bunch of air conditioning around the batteries to keep the battery cool. So that kind of, I would say technology solutions for me as an engineer is very, very, I would say, unsatisfactory for us. So we are really in the special issue, hope to seek out-of-box ideas, people who think energy storage solution from a more holistic perspective. And really the differences between transport here is that we are geographically diverse, just like all the editors, right? So our energy storage solution needs to be robust and resilient in all weather conditions and all geographically differences. So I hope I answer your question in the way.
Yeah, no, thank you. And so, Dr. Baker, I'm going to pick on you for a moment because I know that you've been talking about thermal storage, specifically tied to Northern European locales. I'm wondering if you can motivate the interest and the challenges with that kind of system.
Yes, I mean, certainly thermal storage is a key area in the some of the northern climes, and especially when you look at, do we always keep heat as electricity? Do we turn it into electricity to turn it back to low grade heat? So if we can just keep it a low grade and store. So I think the storage doesn't just need to be how do we store electrons. There's a lot of other interesting technologies out there, some of them very old technologies. Obviously talking about difference in geographies, and hydroelectric has been, is obviously very geography specific, and certainly in areas like the UK we're at a limit now on what we can do with hydroelectric. but what can we also use our unique geographies for? So there are areas of sort of how do we get storage, you know, maybe in old mine locations. So it's interesting to see what are the scenarios coming out specific to people's geography for these long-term storage, because it will not be an application that we can just provide from a factory and ship over the world. I think for these longer distance, longer range storage, we need to look more inventively and use natural resources around that. And I think that also comes back to how do we use natural resources in these storage technologies, and how do we ensure that the embodied energy in manufacturing does not outweigh the benefit of that storage technology, and is there a balance to actually have excess capacity of wind or PV such that you just let it not go to waste, but you build in this loss of power that you won't store everything. And understanding that balance and modeling that balance, I think, is of particular interest going forward, to make sure that we're using our storage as effectively as possible. So having the research in how do we use these technologies as well as the technologies themselves.
Thank you. So to riff on that, and to motivate durability, you brought up this excellent point, Jenny, about the making sure the battery lasts long enough to overcome its initial impact of extraction on the Earth. I want to ask Dr. Jha, where you see aqueous technologies going. Lithium-ion technologies have been dominant for about 30 years now because of their deterministic cycle life and energy profile, even though they eventually die because of consumption of this electrolyte. In theory, aqueous electrolytes should last forever, but these systems yet have not been industrially robust compared to lithium-ion. What can we do in the material science community to address these problems, to get to the entitled long duration, long lifetime that aqueous batteries should allow?
So because we did a long many work on aqueous system, we call the aqueous lithium-ion battery or some aqueous sodium-ion battery. Really, because you know there is aqueous lithium sodium battery in United States. We call the aqueous. What's the company name?
Oh, Aqueon.
Aqueon.
Yeah. Yep.
But you know this company is by Chinese company by this company. But you know they also is produce aqueous sodium or lithium, because really is this aqueous lithium-ion battery because it use a spinel. So we call the sodium-ion battery aqueous sodium. Okay. But maybe it's mixed solutions. But in China now we have one company. I think they can produce like 10 megawatt, like some system demonstrated systems. The problem for these systems is, I think, the cycling life we can get about, I think, about over 3,000 cycles, 3,000 cycles. But the problem is because they have special applications. For the lithium-ion batteries, there is safety problem. There be something worry about the safety problem. And for the lead acid battery, like also some flow batteries, they may be, how to say, also worried about the environmental friendly this problem, like electrolyte pollution, like this problem. But this aqueous lithium-ion battery or sodium battery, because it's I think is environmentally friendly, so it's have a special application. But the problem is the cost is still very high. I think it's at least about, because the specific energy is between, I think, least thing for the about, I think, 30, from 20 to 30 watt hours per kilogram. This is still low. Yeah. So I think the problem is just for these systems is cost is too high because it has a low specific energy. Maybe
Right.
also the material is a problem. The big problem is because since the the working window is too narrow. I think the average voltage about 1.5 volts. So this is a problem. But still have some special applications for this one. So we know there are so many research is moved to the zinc battery, the zinc recharged zinc batteries. So in maybe system maybe about I think can get at least is I think as same as over than 40 watt-hours program is close to the lead acid battery. So maybe have the problem for aqueous systems just is a specific energy is a problem, I think.
Thank you. Yeah, no, so that's an excellent point. This idea that eventually, as we reduce the amount of cobalt in the battery to zero, as we take the amount of nickel out of the battery, the rough cost per kilogram of everything in the battery is about the same. It's not an order of magnitude different anymore. So to Dr. Jia's point, this means that as the energy density of the battery goes up, the cost goes down. And this is a new aspect, because energy density up to this point in time was a premium, and now we're seeing that energy density is actually a commodity. And so aqueous batteries were supposed to save us here, yet when we do the cold analysis at voltages below 3 volts, it's quite difficult. And so yeah. I would encourage submissions on water and salt electrolytes and tricks to stabilize oxygen and hydrogen generation on electrodes, in addition to thermal energy storage routes. Because what we haven't spoke about, and I think this is the last topic of conversation today, is what I've seen in the last decade is really a relaxing on the round trip efficiency. 10 years ago, we expected that renewable energy resources were going to be more expensive than fossil resources, so round trip efficiency was crucial. Now we're seeing that electrons are actually cheaper than molecules at the wholesale rate, with some of my students, graduated students, forecasting 1 cent per kilowatt hour or $10 per megawatt hour by 2050 for wholesale electricity on average, which is an incredible number. So this means that we can potentially trade off some round trip efficiency. To Shirley's earlier point, I'm curious what type of research everyone here would like to see on systems level engineering that can make the systems more robust over time without increasing the capital cost, but maybe by relaxing round trip efficiency. Basically, the only thing we waste is the energy.
So maybe we can solve this problem by the battery design, maybe by using the bi-electrode, maybe so can get it improve its specific energy. I think from the material cost, really we use some spinel. Spinel is cheap, and you can really it's very difficult to find another electrode materials for the cathode material. We tried many sodium-based cathode materials, but also the very poor cycling stability in aqueous systems. But for the negative, maybe use the lithium or the sodium titanium phosphate. So maybe use the zinc. So from the material, it's very difficult to reduce the cost. I think the systems, the problem just is the cost problem.
I think we also need to look at lifetime and also capital cost and investment and how that can be supported. And there are, we talked a lot about, going back to battery systems. There's a lot of electrochemists here, but there are compressed air systems and systems that work directly offshore, particularly. So offshore wind turbines that then have integrated storage with them. That can then as well reduce the installation costs of renewable energy sites, I guess. And so what I would love to see is to see analysis on where storage is located and how that can be used to best reduce some of the infrastructure costs that we might have in terms of increasing electricity availability in rural areas. I work a lot with India, but also mid Wales, very local to me in the United Kingdom, where our electricity grid is constrained when we want to start being able to support electric vehicles. So I think that it's really important to not just look at what storage, but where, and what advantages can be gained at those. So looking at a systems approach of what's appropriate where would be very interesting to see research in that area.
Yeah, Jenny, well said. I completely agree. I just want to add one more point. I think that as a material scientist, you know, for all the energy storage system, regardless is thermal, hydro, or electrochemical, we really have to seriously thinking this as infrastructure, which means decommissioning, recycling have to be within our analysis from the very beginning. So I think, you know, regarding the cost challenge, I do think that for some of the systems, that the upfront capital cost was calculated. However, the decommissioning cost was not. So for instance, the cogen turbines, after 50 years of operations, we still have to take them apart, and then we have to actually, you know, we can't just leave them as a waste, right? So that part of the cost was typically not considered. So we have a beautiful opportunity here. Now we are designing the storage infrastructure for renewables. Hopefully we will do it right this time and really think about the socio-economic impact of the infrastructure that we're going to put in for the renewables.
And I would say sometimes looking at some of the old technology that's been around that can be recycled, things like lead acid batteries, have 99.9% recycled, and are actually, you say, Dan, that lithium-ion has been around for 30 years. Lead acid has been providing that off-grid support for people for more than 50, 100 years, you know. And actually what we can look at is, you know, how can we modernize this old technology? How can it be used for future applications? How can we keep the good bits of the old technology while making improvements on the things that will make it more relevant to the modern situation?
Absolutely. Like, you know, I think it's a time to embrace reaction complexity. We've gotten, you know, intercalates, maybe we're training wheels, and now we have to embrace conversion reactions and their complexity because they provide, you know, at the end of the day, lower cost and theoretically higher cycle life because you get rid of the history. So with that, I hope to the potential contributors to this special issue, you have a sense of what we would like to see, and so much more. We've only really scratched the surface. I leave it with Shirley to finish off the conversation and tell you all about the goals of MRS Energy and Sustainability.
Thank you, Dan. I would just like to reiterate how important this special issue is for us at this very important point where the whole world are looking for solutions to decarbonize our society. So I think MRS Energy and Sustainability has always been the flagship journal for our society and for the world at large to talk about these critical technological, scientific, and the socio-economical challenges. So I hope that we will see many of you contributing to this special issue. Thank you.